Oh, now it's recording. Oh, okay. Thank you, Ashley. All right. So for the first part, we're talking about motion today, but for our do now, we found the average rate of change simply by taking the difference of y's over the difference, in this case, t's. Using the slope formula, we got 3. All right, that was our summation. For the instantaneous rate of change, Jillian, you're just about to tell me, what do you do? Great. Okay, and what do we get for the derivative? It's not looking good. 2t, I don't know why I put parentheses there, but plus 1. And then what do we do? Plug in 1 for t. And so we get 2 times 1 plus 1, which is 3. So the slope of the tangent line at 1 is also 3. If we had this parabola, we found that, okay, the average rate of change over the interval from 0 to 2 was 3. Now we just found out that at t equals 1, the slope of the tangent line is also 3. Crazy. Now, before we go over the homework, I want to just kind of review some basic concepts here. Basically, what the sign of the first and second derivative tell us about a function. So let's say that we have a function whose graph is increasing. It could be concave up, concave down, or just linear. Okay? But if your graph of your function is increasing, what's true about the derivative? Positive. That's it. Remember, the derivative is simply the slope of the tangent line. Better. Now, if we have a function that's decreasing, and it doesn't matter whether it's concave up, concave down, or linear, what do we know about the first derivative? Negative. Oh, that's bad over there. All right, that's a negative. It's not going to be the best recording today. Maybe we can fix it up a little, I don't know. All right, now, let's say we have a function that's concave up. It looks like this. I'm going on, oh, well, looks like that. First of all, let's think about, as we go left to right, what's going on with the slopes as you go left to right? What's going on with the derivative? Well, think about it's actually increasing because it's real negative, less negative, 0, a little more positive. So whenever you have a function that's concave up, the reason it's concave up is because the slopes are increasing. And if the slopes are increasing, the derivative is increasing. Now, I don't have a graph of the derivative, but if I could graph the derivative, it would be a function that's going up, right? It's increasing. And if the first derivative is increasing, what do we know about the derivative of the first derivative, also known as the second derivative? What would be? Well, if the first derivative is increasing, its derivative, the slope of the tangent to this graph, would have to be what kind of a number? Wait, what did you say about 0? Would it be 0, the slope of the tangent? No. Because it's going up, what kind of a number would it be? Positive. So in other words, anytime a function is concave up, it means that the first derivative is increasing, the slopes are increasing, which means the second derivative is positive. So every time a function is concave up, the second derivative is positive. And if the second derivative is positive, that's where your function's concave up. So now, if you have a function that's concave down, that's happening because the derivative, as you go left to right, is what? Decreasing. And if the derivative is decreasing, the second derivative must be negative. I guess I should have written less than 0, but that's good. Okay so far? That's the big stuff. All right, let's just look at the homework answers. Let's get a little full screen on this. Oops, nope. Nope. Oh, I didn't want to do that one. Okay. Can you help me out with the arrow just to get back to the last page? Thanks. Where did this? I'm going to try to recalibrate this. This is just driving me a little crazy today. Fine. Right? Sorry, yeah, just get it out of the way. Thanks. That's good. Yeah, that's a good place. Okay, so let's see. So for the first one, you just had to use the slope formula. For second one, it's the derivative because it's instantaneous rate of change. For the third one, it's the instantaneous rate of change. Fourth, average rate of change. Fifth, instantaneous rate of change. Then you got down to 6 and you actually got to use a real function. And you had to get the slope because they asked you for the average rate of change. So you had to get f of 4, which is 45, subtract f of 1, which turned out to be 6, and divide it by 4 minus 1. So we're just using the average rate of change slope formula, and that was 13. Let me get that one right? Oh, good. Okay. Then for 7, you wanted to find the instantaneous rate of change. So you had to take the derivative and plug in 1, and that you should have got 7 for. So for 7, the answer was 7. Get that one? Okay. Number 8, they asked you, if the first derivative is 0, what does it tell you about the tangent line? Well, that means the slope of the tangent line is 0, so it's a horizontal tangent line. In 9, they said if the first derivative is positive, well, then you know the function's increasing. And 10, if the first derivative is negative, that tells you the function is decreasing. Okay with that? Any questions on those? 11 I thought was tough, and just totally ignore that I put the axis on there because it doesn't matter where they are. The point is, like for the first one, you had to draw a graph whose slope was positive and whose slope was increasing. So you had to draw a graph that was going up, that was increasing and concave up for A. So as long as your graph looks like it's increasing and concave up, you did it right. Because they had to draw a graph that had a slope that was positive, so that meant the function was increasing, and the slope had to be increasing, so that meant the function had to be concave up. For B, we wanted the slope to be positive and decreasing. So the function itself had to be increasing, but concave down. These, I think, were the hardest because of the wording. In C, you had to draw a little graph where the slope was negative, so it had to be decreasing the function, but also you wanted the slope to be increasing. So if the slope was increasing, it had to be concave up. So decreasing and concave up was what you wanted because they wanted the slope to be negative, but the slope to be increasing. Confused with this one or any of them? This one? All right, so C, do you have the words in front of you? What did it say? Okay, so they wanted the slope to be negative, so you want the derivative to be negative. So that means the function is decreasing, okay? And then they also wanted the slope, the derivative, to be increasing. Oh, didn't you say, oh, okay, yeah. So if the slope is increasing, the second derivative is positive, which means the function is concave up. See, as you go, I think you're thinking magnitude, and that's what's confusing you. This is a real big negative number. Less negative, less negative, less negative. Those slopes are increasing, okay? So if the slopes are increasing, that means your function's concave up. And then in D, you had to draw a graph where the slope was negative, so the function was decreasing, and also you wanted the slope to be decreasing, so you wanted it concave down. So you wanted to draw a graph that was decreasing and concave down. That was a little tough. Did you get any of those right, anyone? Yeah? I mean, really? Wow. I think the wording was really hard for a lot of people because it was just, whoa, that's really great if you got that. 12, Okay, so for 12, they want you to write the equation of the tangent line. We love doing that. So you get your y1 by plugging 2 into the function, and your slope by plugging 2 into the derivative. Now, if you wrote it in point slope form, it would have been y minus 1 equals the slope, which was 0, times x minus 2. So if you wrote your answer in point slope form, that's fine. Y minus 1 equals 0 times x minus 2. All right, so to write the equation, you need to get the y1 and the derivative. But if you solve for y, it's just y equals 1. That's the same thing. Oops. And then in 13, they gave you a graph of the function, which I have in black. And they said, how many times does the derivative cross the x-axis, not the function? And so if you think about when you graph the derivative, you're graphing the slope of the original function. So whenever the slope of the original function changes sign, the graph of the derivative will cross the x-axis. So if you look at the function, its slope is positive and then negative. So it crosses the x-axis once here. Now it's negative and then positive. So the derivative will go from negative to positive. It crosses a second time. And then it goes from, I'm going to do my original here. The original function is going from increasing slopes positive to negative, crosses a third time, and then it goes negative to positive, so it crosses a fourth time. So 4 times. So every time the function, the original graph, goes from increasing to decreasing or vice versa, the graph of the derivative crosses the x-axis. Now, there was no 14, so that one was easy. Yep. Yeah. 12, you had to write the equation of the tangent line, right, at 2. So remember, with point slope, you got to get your y1 by plugging 2 into the function. And if you do that, you should get 1. And you have to get the slope of the tangent line by plugging 2 into the derivative. So if you get the derivative, it's 2x minus 4. And when you plug 2 in, you get 0. Okay, so once you have the slope is 0 and y1 is 1, the equation of tangent line is y minus 1 equals 0 times the quantity x minus 2. And this 0 times anything 0, and you could add 1 to both sides. So did you got the right y1 and the right slope? Oh, that's so the last one, 15, I said, don't worry about too much. They just wanted to see, they wanted you to see it, you know, that whole difference quotient, where it comes from. So they said put x anywhere and put x plus h somewhere over here to the right. So h is the distance between these x values. And then you have f of x, which is the y coordinate here when the x coordinate's x. And that's this length here, right? Whatever this number is, f of x, the length of this segment would equal that. And then f of x plus h is the y coordinate over here when x is x plus h. And the distance from that to the x-axis, that would be the distance that would represent f of x plus h. So f of x plus h minus f of x is just this distance between them, right? You know the whole thing is f of x plus h. This part's f of x. So f of x plus h minus f of x is this length here of this segment. And then if you bring it over, you see that's just the change in y's. The h, that's just the change in x's. And when you use the slope formula, you put change of y's over change of x's. That's how you get the slope. I just wanted you to kind of see where all these values come from. This one I wasn't too worried about it because I think the wording kind of threw you here. But you get it, though? I mean, it's just kind of what we did. All right, you ready for some motion? How many people have taken physics? Oh, all right, let that be a warning. You guys have taken physics, some of you, huh? Not everybody. What's that? Oh, physics. Well, in this class, we're only going to talk about, oh well, what we call rectilinear motion. And what that means is we're going to talk about an object that's moving, but along a straight line. That line could be a vertical line, it could be moving up or down, or a horizontal line, moving left and right. So just think you've got this object and it's moving along a number line. Bless you. Could be moving along a vertical line or a horizontal line. It doesn't go off the line. Okay, so it just moves back and forth or up and down. We have to get some terminology down. And the first thing we have to talk about is position. Now, in this class, we're going to use either x of t or s of t to talk about position. In physics, what did you guys use for position? Do you remember? Oh, d or x of t? Okay. Well, here it's going to be either x of t or s of t. And what it means is the position at time t. We use function notation because that position can change. So if I tell you, let's say, s of 3 equals 5, what that means, when the time is equal to 3, so 3 seconds into my trip, am I going to reach this? Nope, I'm not going to, well, maybe. I'm at 5 on the number line. I can't do it. I can't do it. All right? But it's just telling you where you are in your number line at a particular time. That's all. So since my position could be negative, position can be negative, I mean, you might get a negative number. Next little. Velocity is the rate, the ratio of change between position and time. You've all heard of velocity, right? Before? So we have a special name for that ratio of change of velocity with respect to time. Now, if that rate, change in position over change in time, is positive, the change in time will always be positive. So if you get a positive value for velocity, that means that the change in position must be positive. So you're moving right. You know, if you're going on a number line, if the change in position is positive, change in time is always positive, the velocity is going to be positive. So what you want to know is every time you see a positive velocity, your object's moving right, if it's moving left or right, or up, if it's moving up or down. And if your velocity is negative, which way would it be going? Down or left? You know, it just depends whether the line it's moving on is horizontal or vertical. Acceleration is the rate at which velocity changes, so it's change in velocity over change in time. And if, again, change in time is always positive, so if the change in velocity is positive, acceleration will be positive. And so that'll happen when you have some force pushing something to the right or pushing it up. Right. Now, we said position tells you where the particle is on the number line. We use either s of t or x of t. Related to position, we have the term displacement. Displacement on, this means the interval from time equals a to time equals b. So and the way you find it is you take your final position and you subtract your starting position. So let's say I start out on the number line at -4. I'm stuck over here. And I move over to position of 0. What would be my displacement? Which one? Well, the final position is 0 minus the starting position. So it's -4, so that's going to be +4. And what that's telling you, basically, you moved 4 to the right because you got a positive number. What if I started at 6 on the number line and I ended up at 0? What would be my displacement? -6. Basically, you wound up moving 6 to the left. But it's final position minus starting position. Okay. Well, you must have seen that somewhere. Well, that's what it is actually, because when we get a negative value, basically means the net change in position is to the left.
Yeah.
Oh, yeah, the vector.
It's a scalar.
Yeah. We're not even going to be using vectors in here, so don't even worry about it. Now, here's something to think about. Distance is, so displacement can be positive or negative. Distance is always positive. Now, I'm going to see if you can figure this out. Set up a little chart for me and label it T and S of T. And I'm going to give you the positions at 3 times. We need to know what the position at the start time, I'll call it. Let's say the start time is T equals 0. And let's say its position is 5. So it's at 5 on the number line at time 0. I also have to tell you where it is anytime it turns around. So I'm going to call this a turnaround time. Turnaround time. And let's say it turns around when T equals 4. And it's at -2 on the number line at T equals 4. So it starts out at 5, and it goes back to -2, turning around. And then it ends, the finish time is at T equals 10, and its position is 12. So it's at 12 on the number line at the end of its little trip. So it starts out at 5, over there, goes back to -2, and then goes the other way to 12. And we want to find the total distance of travel. When it's starting out, is it going left or right? Left. How far is it going? The first leg of his trip when he's going left. 7. So to figure that out, you subtract and you just take the absolute value of that difference. Distances have to be positive. So if you do 5 minus -2, you take the absolute value of 7, or -2 minus 5, absolute value is 7. Now, it's at -2, and it goes right to 12. How far does it travel? 14. So altogether, how far does this object travel? 21. So we can find the total distance using the position, but the only way we can do it is if we not only know its position at the start, at the end, but any time it turns around. Because if you didn't know where it was when it turned around, if all you knew was where it was when it started and where it was when it ended, what would you have said? 7. That's just the displacement. It's not the distance. Now, sometimes if it turns around, they're not going to be the same value. All right. Now, this is where it gets really fun, and they don't talk about derivatives in physics. So velocity, we know, is the change in position over change of time. And you've probably done this many times. If you put a little line over it, this means just the average velocity. So up until this point, you found like the average velocity by taking the total change in position over the total change in time. What you've been finding is the slope of the secant line to the position graph. All right, like if you add the position graph, position as a function of time, you've been finding when you find average velocity from A to B is the slope of the secant line. 2 points, use slope formula. But now, with calculus, you can find the instantaneous velocity, or what we call just velocity, which is not delta S over delta T, which implies that they're 2 different positions, 2 different times. We're going to find the slope at a single point. When you find the slope of the tangent line to the position, ds dt, you've now got the velocity at a particular moment. You've got, when you look at your speedometer, you don't want to know your average velocity for the last 10 minutes, right? You want to know your velocity at that moment. And that's what the instantaneous velocity is. It gives you the slope of the tangent. It'll tell you velocity at that moment. So this is pretty powerful. So if you know the equation for your position, just take the derivative of it. Now you got an equation for the velocity function. How crazy is that? And you might be wondering, oh, how am I going to remember this? Well, if you know that velocity, average velocity is delta S over delta T, velocity is ds dt. It's the same thing, just instantaneous. Instead of the deltas, you have the differentials, the ds and the dt. It's good stuff. I mean, it's so fun. And the other thing I just threw in here, velocity can be positive or negative. Speed's always positive, so it's just the absolute value of velocity. Have anything on here? Okay. Acceleration is the ratio of change between velocity to time. So it's a change in velocity over change in time. So anytime your velocity is changing, you're accelerating. And just like, so this part you know that the average acceleration, you take the change in velocity over change in time, right? It's just the slope of the secant line of the velocity graph, your average acceleration. Well, we don't want to just know average rates of change. We want to know instantaneous rates of change. The instantaneous acceleration, you just use the differentials instead of the deltas here. It's the derivative of the velocity. Wait till you see all this together. Let's do this together. Okay. So what this is, have you heard of SPOT before, SVA, or like the way you remember? I've never said SPOT because usually Corey loves that. So when you take the derivative of position, you get velocity. And the derivative of velocity is acceleration. Oh, so you couldn't use it. And that would be like, you can't even pronounce it. Yeah, that would be like another. So whenever you want to go in this direction, just take the derivative with respect to time. So derivative of position is velocity, derivative of velocity is acceleration. So acceleration is the first derivative of velocity, but it's also what? Second derivative of position. I mean, if you've got the position function given to you, you take the derivative once, you've got your velocity. Take the derivative again, you got your acceleration. Can you believe this? No, he's not here today. No, just kidding. Yeah, when acceleration changes, the change dA dt is called a jerk. So, but yeah, we won't talk about that too much. That would be the third derivative of position. We only go up to acceleration. So yeah, that's how you're going to come up with other equations. And one way that people use to remember this is an acronym SPOT. In other words, see, the S is for the position, V for velocity, A for acceleration, and the T just means with respect to time. It's not dx, it's T. So what are you talking about? We're talking about motion. That's how you're going to remember that. It's the order. I don't know if I'm going to be able to do enough to. I might actually let you guys off the hook, but maybe. Let's try. Let's see what we can get from this. What did I do here? All right. Move that. No, don't ever say give up. Okay. Oh, did you hear what Ashley Hawkins just said? Ashley Hawkins just hurt my feelings. Okay. So in this one, given the position, find the average velocity on the interval from time 0 to time 5. How do we get average velocity? Change in what over change in what? Yeah, it's change in position over change of time. So we'd have to get the position. We actually have to figure out the position at time 5 and subtract the position at time 0. That would be the change in position, right? And what do we have to divide by? Change in time, so 5 minus 0. S of 5, when you plug 5 in for t, oh, it is 21. Did you just do that on your calculator or in your head? Oh, you did. You went ahead. Oh, that's good. So that's 21. What about S of 0? That one you can do in your head, right? S of 0 is uno. Okay, I just got that. All right, over 5. So what did we get for the average velocity? 4. Yeah, we don't have units, but it'll be something like meters per second. Oh, that's just an average velocity over an interval. What about if I ask you for the velocity function, v of t? How are we going to get that? It's derivative of the position function. So what's the velocity function? Yep, which is 3t squared minus 12t plus 9. I guess I should have written dsdt. Oh, that would have been nice, but you see it. Now we have a velocity function. So now I could ask you for the average acceleration on the interval from 0 to 5. How would you get that? Change in velocity over change in time. So, wait a minute. Yep, that's what the average acceleration is. So you would have to get the velocity at time 5 minus the velocity at time 0 over 5 minus 0. Big, huge problem. You see it? I'll get rid of this. It's too much stuff. V of 5 minus V of 0, I think it's 24 minus 9, into the velocity function, which you just got by differentiating the position function. And we get 3. Circling that, I'm going right to the bell. How do I get the acceleration function? That's derivative of velocity. 6t. So acceleration at time t is equal to 6t minus 12. It's enough. Do as much as you can. There's one problem like this, but try to get at least as far as we got. Those 2 problems, right? You ready? This is a fun unit. It's only a week, but yeah, don't be intimidated, other kids who didn't have physics. I'll be a little. Thanks, guys.